My name is Dr. Alfredo Carpinetti.
My name is almost Dr. Matt Yeh. Matt Yeh? We're off to a great start! My name is almost Dr. Matt Young, and today we have a very special guest with us.
I'm Dr. Duncan Astle.
And why don't you tell the good people at home what you do? Where are you from?
I'm from Cambridge. Come all the way on the train, and I work for the...
Thank you.
I work for the Medical Research Council at their Cognition and Brain Sciences unit, where I study the brains of children. How much detail do you want?
That's good enough. That's good enough to start with. We'll go into more depth later.
Yeah, strong start. And when you answer a question, you can tell us a little bit more about what you do. So,
if you are new to the Astroholic, to let you know, we will be chatting a bit of science, making a few cocktails, as you can tell, and as always, we are answering some of your questions you've sent us already, but we're also looking for more and some great science puns and innuendos along the way. So do tweet them to us at, and I get the hashtag wrong every time, hashtag #TheAstroholicLive, or you can tweet it directly to us. I am at MattJY and
at Dr. Carpinetti.
Yep.
So, the Astroholic is probably easier to spell, but
yes.
Since you got the hashtag right, you get the first gold star.
Oh, thank you. You're too kind,
I am very, very kind.
Like working at McDonald's with the gold stars.
Did they get a gold star?
No. I had no idea.
Moving on.
Says Duncan as he covers up that shameful part of his employment.
I've never worked for McDonald's.
And there is no shame in honest
there's no
employment.
shame for anyone who has one.
No. Yes, I think that's important to state.
Anyway, let's start by talking some science. Do you want to start with some science news, or should I start?
Why don't you start today?
Alright, so there are a couple of interesting science news from the last couple of weeks. We haven't had Astroholic in a month, almost less than a month, 3 weeks. And so there are not been as much science news as there usually are, but my favorite piece is from a couple of days ago, and it's about dark satellites. What is dark satellites?
What are dark satellites?
Yeah,
there we go, thank you.
Anyway, dark satellites are clumps of dark matter that orbit galaxies. Big galaxies like the Milky Way have a lot of smaller galaxies. They're small companion galaxies. They're called satellites. They're called dwarfs galaxy because they're much smaller, between 10 times smaller to over 1,000 times smaller. There is this idea that dark matter can sort of clump up in larger distribution, or well, the same size of this satellite galaxy, and once in a while they interact, and suddenly you have a burst of star formation. So in this small galaxy, you suddenly have a lot of new stars, and we don't have a mechanism to explain otherwise how this tiny little galaxy would form so much stars, unless there is this big gravitational interaction. And it's very interesting because we cannot see this dark satellite. Even in direct measurement is very, very difficult, but we can measure the effect and the type of, can predict what kind of universe would have this kind of object in, and it looks very much like our universe. So, although there is very little observational evidence that this dark satellite exists, models tell us that they should be there. So we should look at them.
How do you measure them? Their presence?
So, ideally, you would want a system that can look at the minimum changes in gravitational in gravity. So anything with gravity can create a gravitational lens. They're so small that what you would be looking at is called microlensing. So small variation of light from distant galaxies. But there are also other ways. Gravitational waves can be used to measure this object, both directly when we'll have a more sophisticated system to measure gravitational waves, but also you could measure the travel time of gravitational waves through these clumps of dark matter. But also you can do it with, if you had a gamma ray burst, which is a very energetic explosion, you could measure how long how much the light is stretched across the universe, because when light goes through gravitational well, it's like going.
What is a gravitational well? It's like
when there is matter, the space-time is curved. So instead
not quite something you'd like chuck a penny in and make a wish.
Yeah, no. So
okay.
In the usual.
Thank you. See, I'm funny. Carry on.
Are you? Anyway, instead of thinking of space time as flat, you can imagine this curve, and light follows the curve. It wouldn't go straight, so you can calculate there is a sort of delay. It takes more time than you would expect, and it's telling you that there is matter.
So with something with stronger gravity, a stronger gravitational force, the light would follow this curve of space-time. It would kind of go.
Yep. And so.
With that sound, right?
With that sound, exactly. That's absolutely correct.
These are facts.
Yeah.
These are facts.
And,
hard facts.
So there are, these clumps of dark matter are just too small. They're about very similar to the size of the satellite galaxy. So 1/10 to even 10,000 times the size of the Milky Way. So quite small in comparison, but quite big in comparison to us. So.
But there's a lot. Everything is big in comparison to us. We're just the very narcissistic speck in the universe, aren't we?
Absolutely. Well, we are the universe knowing itself.
That's
very good.
That's too deep to go into before we've even had a drink.
Okay, so should I make the first shot?
I think we should go for it. But Mr. Dr. Carbonetti,
good correction there.
Maybe that's what I was going for. He's not told us this week what we're actually going to be making.
Well,
so please enlighten us. He said it's a surprise.
Well, the idea is we have a lot of alcohol to use from all the previous Astroholics, so I'm just going to use it, and we'll find out what we get. So the first one I just invented like 10 minutes ago. It's called a blue gin.
But we are professionals, so we prepared.
I'm going to try and get the train here later, so get that in early.
Well, are you driving the train?
No,
so
exactly. So you can have a shot.
Great point.
I'm not sure what you're implying with.
What's that?
Blue Curacao. I call it. It's a blue gin. Or blue jeans.
Blue jeans.
Hey!
Science joke.
More fashion joke, I guess.
If you're into that kind of stuff, but we don't talk about that here because
we don't know anything about it.
Nope. I only know what you can buy at Primark, and that's a sad insight into my life. But I am very looking forward to drinking these and not rambling on anymore.
So this is a blue gin.
Blue gin, fantastic. But we always like to cheers to something. Our last guest kind of shotted everything way ahead of anything we did. So what should we drink to this time?
The dark matter.
The dark matter.
Cheers.
Cheers. That's actually really nice. Normally I have to kind of forget a bit and be like, yeah.
I don't think Duncan agrees with that.
It's great. It's nice.
No, it was really nice. It's it went down a treat.
So
tingles.
Tingles indeed. Would you like to go with the next news?
Yeah. So coming from the world of biology, grounding us, coming back down to earth. I have read an interesting story this week about a particular advance in neurodegenerative diseases, particularly something called Huntington Disease. It's a very strange disease in that we don't entirely know how it works, what's going on, but it does affect a fair chunk of people. And what happens is in their old age, they start to lose a lot of their long-term memory, which is very sad, because what you see in other diseases, particularly like Alzheimer's, is people will start to lose a lot of their general brain function in different areas, but Huntington specifically seems to be focused on memory, which is quite tragic for family members and stuff. And it all comes down to this mutant protein called HTT, or Huntington protein. But no one really knows exactly what it does. It seems to have a role in maybe like connectivity and synapse function. And people have tried for a very long time to figure out what it's actually doing and what's going wrong in it in these cases of Huntington's disease. So, along comes some scientists, and they...
The scientists.
Yes, hooray for science is always coming to the rescue. You know, basically superheroes, not all that. I'm sorry, I'll just come in there. Anyway. So, what was I saying? Along came the scientists, and I have the names here of where they were from. No, I don't. Great. But anyway, they thought they'd implement gene editing. So, gene editing, been all over the news lately. Everyone's like, ooh, gene editing. But mostly it's been people panicking like, oh my god, designer babies. Let's create some horror sci-fi situation. That's definitely what's going to happen. And obviously, that's exactly what's happened here, except it hasn't at all. Because what they've done is they've set up a really interesting animal model. Why are we getting booed so much? Come on, man.
Our sound technician is getting good now. Okay.
So those boos were not towards the advances in science. I'll just have you know that was a technical hitch.
So animal model.
Yeah. So what they've done is people managed to find this animal model using mouse because there's a lot of mouse models of Huntington where basically mice have been engineered to have this their version equivalent of the Huntington gene be mutated, and so they exhibit the same functions. But what they managed to do, they managed to edit the genome in such a way that they were able to block the expression and basically the use of this gene in mice. So what they did is they blocked it in some young mice, so it wasn't used at all, and then they blocked it in older mice. In the young mice, it was tragic. So they didn't develop properly, they developed all sorts of complications. So they realized, okay, whatever Huntington does do, it's important when you're young. But in the older mice, and that's kind of a good analog for in humans, when you get Huntington's disease, it's often a case that symptoms appear in old age. They blocked this gene, and mice didn't degenerate. And it's really fascinating because they used a mechanism by where, in the presence of this particular estrogen-related drug, they managed to block any sort of use of this protein. And the mice didn't experience any side effects as such from that. So, I mean, of course, to edit genes in humans is like crazy impossible to even think about doing now, especially adult humans. I mean, an embryo is one thing, because it literally is one thing. But to then try and do that in humans is totally another story. But this is a great first step, because it's the first time people in animal models have managed to effectively halt the onset of this disease. So it opens up a whole new window of opportunity and discovery, really, to look into. So I found that really fascinating.
That is absolutely fascinating. It's very interesting and very important that we invest in therapy. There are a lot of autoimmune disease, for example, that could benefit from having developed gene therapy in adults. When we discuss how to change or improve our genes, is mostly in adults. No scientists care about the sign of babies. No scientists. We want healthy people. We want people healthy that are living, that are struggling to. Right now, it's one of the consequences of science is that we can try to make the world a better place, and to the people that live in the world. I haven't finished.
But thank you.
No, it's important, and I think there's a lot of misconception on every time that we talk about genes.
Yeah, people have. I don't know about your field, Duncan, but have you ever had that experience of talking about your work to people and mentioning genes, and they're sort of people having sort of quite serious preconceptions about it, saying, "Oh, you're looking into genes. That's forbidden territory."
I guess in our case, it's more the situation where when you describe, I don't know, a difference across kids in terms of their brains and how they work, they often just say, "Oh, well, that must be the genes." And they've got this very kind of simplistic, reductionistic notion of how genes work, and they don't realise the kind of more complicated way that genes can interact with each other. Genes can interact with the environment.
Okay,
So how does it work? So in the brain are lots of neurons, and certain neurons, called pyramidal neurons, are lined up so that the axons that stick out of them all line up alongside each other. And that means that when they become active, they generate a large electrical current.
Can you explain what an axon is to our audience?
An axon is a part of the neuron that becomes heavily myelinated.
So basically wrapped in loads of fatty stuff.
Yes.
Yeah.
And it's
Like is
the long thing that comes out the back end of it. Is probably the way to go about it.
That
Yes.
was perfect.
Yes, perfect.
You get a gold star for that.
And whenever you get an electrical current,
Mm-hmm.
physicists among us, what do you also get?
A magnetic field.
Yes, which is the
Is
GCSE
perpendicular.
physics.
Yeah, I did that thing.
The right-hand rule.
The right-hand rule. Why don't you explain it? Because obviously you work with this stuff and I don't.
Well,
I just
this
remember
is-
doing this.
I want you to explain this. Also, for magnetic field, you can also use.
Is that okay? No, let me try. Is that because magnetic fields form at right angles to each other, or something like that?
Yeah, close enough.
Close enough. Close.
So, electric.
Look at me doing physics.
I feel we've been slightly sidetracked.
Yes.
Right-hand rule.
Actually, on that point, we did actually get a. Sorry to interrupt you, but we did actually get a mention from somebody at kcog_ who says the sound effects are on point tonight. So thanks, kcog, and your name is just G&T, so I don't know what to call you, but thanks. Our sound tech guy is pleased. But back to our
Right-hand rule.
Yes.
right-hand rule.
So anyway, get these magnetic fields emanating from the brain as the electricity goes through the axons. And if you sit the kids in a scanner and you kind of crank the chair up so that their head sits inside a helmet, and on the other side of the helmet, these little coils called squids, which stands for superconducting, oh, I can't remember, quantum interference devices. Superconducting quantum interference devices.
That spells squid.
Anyway, so they're bathed in
Squid
liquid.
enough. Squid enough.
They're bathed in liquid helium, which is at minus 270 degrees.
Mm-hmm.
They're exceptionally cold, which is how they become superconducting. And they're so sensitive that they can detect magnetic fields emanating from the kids' brains. And so we scanned the kids with this technique before and after the training. And we were able to show that not only did they get better at working memory, but there were some important physiological changes in how their brains were working in the areas that we think are to do with working memory and attention. So that was all good. The slightly controversial thing is that lots of people have made very strong claims about the potential therapeutic benefits of that kind of training. So they have said that you could use working memory training to remediate cognitive problems that people have and that children have. But the problem is that the evidence base that they use to make that claim isn't very good. So they use studies like ours, which wasn't designed to test those therapeutic applications in any way. We don't even include any wider measures. Or they cite studies that aren't tremendously well designed, like studies with no control groups, or where the children aren't randomly allocated, or where the assessors aren't blind. And we know that all of those things can make very big differences.
Especially the no control group thing. And
Don't
do you
start about no control groups.
What? Yeah, surely that's like the biggest faux pas in science. No control group. I mean, what do you compare to?
You compare to the same kids before, oh, they got better. We can conclude that it's our intervention, not that they're a year older. That's the level of... Anyway.
Yeah.
Yeah, that's.
Yeah, but by that method, I can just conclude whatever I want from anything. But anyway.
So, this week, a randomized controlled trial came out. The randomized controlled trial is really the gold standard in testing an intervention. And it's a really big study. So they had 200 kids in the control and 200 kids in the active training group. And they followed the kids over 2 years. So it's a really major enterprise. And they importantly included things like maths measures. And so what they wanted to test is, do kids get better at working memory? And does that transfer to actually something you might want kids to get better at, like maths? And so they tested them after 2 years. And what do you think they found?
It didn't help.
It didn't help. In fact, the kids in the intervention actually were significantly worse
Wow.
at maths. Yeah.
Ooh, yeah. That was pretty sucky.
But the working memory got better.
So the working memory got better initially, and that lasted up to about a year out. But by 2 years out, those changes have gone. And not only are they not any better at maths, they're actually not massively, but significantly worse at maths. And so Guy's question is, why is it that we know that working memory is a really great predictor of maths, but that if you train kids' working memories, they don't spontaneously get better at maths?
That is very interesting.
Good question, Guy. So I think the answer is that when kids develop normally, typically, these things develop hand in hand. So the working memory demands and the learning of maths go hand in hand. And you can't just train working memory in isolation and expect that playing games like shooting asteroids and stuff, even though it taxes working memory, will spontaneously transfer to math. The kids won't suddenly start using these skills in that domain. If you really want to enhance maths, then I think your intervention will have to involve maths in some form. That you'll need to embed the training alongside the actual learning activities themselves.
So I guess it's almost like a type of exercise. You can't expect to just, I don't know, lift one weight on your left arm the whole day and then, oh, all of a sudden my whole body is strong.
Exactly, yeah.
You have to, I don't want to use the word holistic, but you need to have a more complete
holistic,
approach.
So it's interesting because in our field that's quite controversial, but in the field of like neuro rehab, the idea that you would train something like with a patient for 10 sessions in the lab or in the clinic and then just go, off you go, good luck. You would have loads of sessions where you try and encourage them to use those strategies in the real world so that they make those links. And I think something more like that is going to be needed if something like working memory training is to be effective.
Well, that's very interesting.
Yes.
And hopefully someday we can figure out a strategy to do that so future children don't have to do horrible remembering to their times tables parrot fashion.
I sense you're slightly bitter about that.
Maybe a little bit, maybe that's what I had to do. Yeah, that applause. I will dedicate that applause to my mum for forcing me to literally learn all the times tables off by heart, not actually understanding them at the time, but just being able to repeat them, because for me, maths was really hard as a kid. If we had like a working memory intervention that would really focus on the maths, that would have helped kids like me, because I just struggled to grasp it much as a child.
We have a clinic and we take referrals from various places. Not for you, but what I was going to say is
I'm actually a little disappointed because I was getting hopeful there. I was like,
you're actually outside our age bracket, but
no. I mean, do children at heart count?
Yeah.
Yes.
What I was going to say is that the majority of the children have problems with maths. So it seems to be a really common thing that all the kids that are referred pretty much have problems with maths.
To be honest, is we teach maths in one way, but kids don't learn in a single way. And maths is something that people don't question how it's taught. It's you start with addition, start with basic geometry, and you start with times table.
When you say kids learn in different ways, what do you mean?
Kids don't, as having taught kids, not all the kids see, oh, times table, if I memorize this, I can do every operation.
Okay.
They just like, oh, I need to memorize this because my teacher wants me to memorize this. It's, oh, if I can, not every kid has the sort of power of abstraction connecting the dots. And not even every adults, but most people doing maths more and more, they eventually makes the link and things they did in the past become clearer. And I don't know, it's sort of...
One thing I find quite interesting, which is kind of related to the topic, is that it kind of dips into cultural stereotypes, but there is some truth into it in the fact that people from countries, from East Asian countries with pictographic languages tend to be a lot better at maths. And there is some kind of a link there because their language themselves that they actually use is... there's been studies that show there's like a completely different brain area that is processing their language compared to, say, Western languages, because it is very pictographic in terms of the characters, like in China and Korea. And so I'd be very interested to know if there's like a link in that way that could maybe help kids. I mean, no, it's not a definite rule, but it has like seen some correlation there.
I guess it depends when you say learning maths, what you mean, whether you want just rote knowledge of facts or whether you want kind of understanding. And so there's lots of, in Eastern culture, there's a very heavy emphasis on kind of very directed maths instruction. But that really is a very different type of maths learning to the type of maths learning that might be encouraged elsewhere.
Yeah, that's a very good point.
So
And-
leave it on that bombshell.
On
yeah, and actually we've had a tweet from @JD Yates. Hi JD. He's literally just tweeted the hashtag remedial maths.
For you.
Targeting at me.
Great pun.
So thanks. Great pun, great read.
on
Keep your shade to yourself.
yeah.
But let's move on from this horribly
Yes,
sore topic.
So the next shot is gonna be rum, and it's gonna be apple sour, and it's gonna be a sour pirate.
Ooh, I like that one. A sour pirate.
Say that now.
No idea the context of that one.
Sound is on point tonight, and yes, and after that we're actually gonna answer. I'm gonna answer the question that JD put me through a couple of days ago. So
Well, it's at this point as well. We'd like to remind any of our viewers at home, all two of you, that we are always looking for any good sort of science jokes or puns. But also, do send us your questions. If you've got any questions about what we're talking about tonight, any questions for our special guest, expert cognitive neuroscientist Duncan, please do send them in. Tweet them with the hashtag #TheAstroholic Live. And yeah, we will endeavour to answer them tonight or give you a shout out because, you know, who doesn't love a bit of interaction? Eh?
So
The colour of this is not dissimilar to that stuff at the dentist.
what's up with dentist? I was thinking
What
more
dentist
like
have you been to?
The ones that use mouthwash.
All the ones I've been to, it's pink.
yeah.
That's green at mine.
I think you should have words with your dentist.
So cheers.
Cheers.
To maths. The cause of, but solution to a lot of problems. Yes, thank you. I just got mimed applause from our audience in here. Thank you. I'm sorry no one else appreciated it. That was tasty.
I prefer the first one.
I do, but this was also tasty.
So JD asked me about planet called Format B. It's mostly known for as the Eye of Sauron. It's in the system. It's going to be tweeted in a second. In the system, there is 3 stars, and around 2 of them, I think, we have found planets. So his question was, if you have such a complicated system, how can you have planets forming? So, have you guys heard of the 3-body problem?
Probably not in this context.
No.
What would be your solution of the 3-body problem in another context?
Send us your solutions. How to use
I'm
the
assuming-
3-body problem. No context.
Duncan is implying anal, but anyway.
Whoa! Moving on.
That's where the shame bell should be, but anyway.
This is where we try and raise our presence completely from the internet and start over. Thank you, Alf. Shall we continue with the science?
The interesting science about these 3 stars is, although they're quite far apart, wow, you guys really weren't expecting that, although you were thinking that.
Thinking it and then saying is another thing.
Well, the 3 stars are quite far apart. One of them is as far from this planet as the Sun and Alpha Centauri, which is the closest star to our solar system. I'll repeat that: Alpha Centauri.
Alpha Centauri. Alpha Centauri. This is not Italy, Alf. It's Assimilate. Come on. I did, you can. Is that meant to be the trumpets of British imperialism? Why is that sound so long?
Okay.
There we go.
They're quite far apart, but the central star is big enough to overcome or overpower the gravitational attraction of the rest of the galaxy. So the system is gravitationally bound, although very far apart. So there is no problem for planets to form. They might have a significant interaction between the stars, so they might have some sort of perturbation, but we don't think there is going to be any problem. They're not really close.
What? Sorry, what do you mean by a perturbation there?
So,
Between them.
the system is gravitationally bound. So the three stars are, although they're far apart, they cannot be separated. So they interact with the rest of the Milky Way, but they move as a single body.
Okay.
At least for now. Probably they're going to be separated eventually. And it's the question that JD put forward is what happens to the planets? And the planets shouldn't be affected too much. So you might have an orbit that is slightly elongated, you might have an orbit that changes as the planet goes around and interacts with the other gravity, but they're really far away. And gravity scale as the square of the distance. So if something is twice as far, gravity is 4 times less strong. So it's very interesting, mostly because the picture of the planet that we got from infrared light looks like the Eye of Sauron, but also because it tells us that the planet can form in a lot of more extreme environment, that the solar system is not special.
That seems a bit mean.
But we shouldn't be special. For as
It's
much
more
as
exciting. There's potential that there are many.
I know, but what can I say? You know, we're a narcissistic species.
Yeah, but
I've mentioned that before.
I subscribe to a soft anthropic principle, so we cannot be special. The universe has to be has to be a little bit special because it can involve a sort of intelligence life like us. But
Sorry, I looked at that.
but it's
Is that because maybe you met some non-convincing examples of intelligent life here?
well, I said sort of because that's clearly
There's nothing wrong with being bad at maths.
Yes, exactly.
Whoa! How did we just turn on me all of a sudden so quickly?
Sorry.
That is not cool. That is not cool, guys.
Anyway,
okay.
it's
Species on species crime here. I mean,
the universe. As far as we can tell, the universe is quite special for us. There's a lot of big cosmological parameters that tell us that we are a bit special. But the solar system shouldn't be that special. We can see that there are so many planets out there, and we only started looking for planets properly for the last 5 years. And if all the candidates planets are confirmed, we have 5,000 planets in our neighborhood. They could be 100 billion planets in the Milky Way, if not more. So why should we be special? But it's interesting to find these sort of limiting cases that tell us that planets are a lot more resilient, or at least planets can form, maybe not thrive or not stay there for long around a complex system, and maybe life can be as resilient.
very interesting. Very interesting.
Yes, I hope JD that answered your question, and
that provides an interesting segue into talking about aliens again.
Talking about aliens again.
Yes, we are going to talk about aliens. So, actually, before we go, are we going to have another drink?
Yeah, we can have another
I
drink.
think that would be a great opportunity.
Yes, because
like we need
we're
an excuse.
talking a lot, but we're not drinking enough, I think.
No, and I'm pretty sure we've had that complaint before. Saying you don't drink enough. You talk too much.
Yeah, probably people that saw
Yeah,
the
not like
first.
this is a talk show or anything.
Yeah, that saw the
Erroneously
first.
tuning into science.
They just want to see us get hammered.
They probably saw the first Astroholic and thought, "Ooh, that is fun."
Yeah, they're going to continue down this route.
So I haven't done the first one?
I couldn't speak anymore.
No, and I don't remember what I said on the first one. Like, we're professionals now. We won't go back to those times.
Yeah, the problem is to start it off, we had 8 shots each.
Good grief.
So
How about we tone that down from like a 20 to like a 4?
So the last one is gonna be, I'm gonna call it dark matter, and because I started with dark matter, but also isn't the brain a little bit like something mysterious? And help me here because it does.
No. I want to see where you're going with this before I jump in.
No, it's fine. So it's gonna be vodka,
He says
glucose
it's
and and Merlot grape juice, which apparently is everyone mentioned that it is not as nice as waitress made me believe. So, well, we'll find out in a minute. To be honest, I'm sure that this is not the worst cocktail that I prepare for the Astroholic, so...
Matt, what is the worst cocktail?
I think last time...
Yeah, well, last time. To be honest, it sounded great in principle. It was something
That
with
jam thing?
No, actually, that jam thing was super tasty. Like, it was really nice.
Rude about throwing shade on the jam thing.
Exactly. But...
The jam thing looked great.
Now he changes his tune. No, but the other thing with the... I mean, I was very impressed.
So...
Alf was like, oh, look, I've made, what was it, like a lemon syrup or
It
something
was
like that?
Earl Grey lemon curd syrup. The problem with that
rum,
was...
I think, wasn't it?
Huh?
With rum.
We mixed it with rum, but the problem with that is that I thought that the syrup wasn't going to be citrusy enough, so I added lemon, which made it very acidic, or as Matt described it afterwards, as acidic as sick. So...
It was awful, basically. Seriously, what is with that stuff? That noise, like... I think it's setting the slightly the wrong tone for the show. I mean,
So, it's not finished.
oh. Nice deep purple for deep space and deep conversations.
And dark matter.
And dark matter, of course. You look very professional there with your really long spoon.
Don't you know? Thank you.
That wasn't even meant to be a joke.
So, our third cocktail for the evening. What are we doing?
Oh yeah, that's a good point.
Quickly before the drum roll ends.
I don't know why you were looking to me.
To aliens. We are going to talk about aliens.
To aliens.
Cheers.
May they exist in some place.
Oh, it's nice.
You sound
It's a
surprised.
surprise.
No, that is very good. You have outdone yourself tonight.
Thank you.
I think the
Yes,
Merlot-
many applause to
The
Dr.
Merlot grape
Magnus.
juice
It's
is a
actually
perfect. Yeah.
So,
I can't help but feel like
There
grape
is a
juice is just
poster.
grape juice, but who am I to say
You shop at Waitrose.
no?
There you
It
go.
doesn't look like I shop at Waitrose. I am a PhD student. I cannot shop at Waitrose.
so tell us about aliens, Matt. So that's what you're trying to tell us.
So, aliens. Yes, well, on the basis of thinking, oh, what life could be like out there, you know, we've discussed this many a time and we've touched on extremophiles, but we haven't touched on our favourite creature. And Alf and I were actually at the Royal Institution last night doing a bit of science, doing some tardigrades. So here we have Tabitha,
Yeah.
our 3D printed tardigrade.
It might have been to pass along to get closer to the camera.
Yes, please. If a cameraman, if you could just give us a close-up very briefly. But and I'm hoping we'll focus. Will we? No, there he is. Woo! Yeah. So that is Tabitha, the tardigrade, and tardigrades are actually of very particular interest when it comes to survival in space and speculation about what life could be like on other planets.
Are they gender specific? As in you call it Tabitha.
I don't know. I just thought it was good for the alliteration.
Okay.
We
Yeah,
just decided
Tony.
It could be Tony. We don't, we don't
don't
like,
need-
we don't want like to gender it. We just
Okay,
like the name
fine.
Tabitha. So
Gender neutral.
Tony, Tabitha, or
Tony
I don't know.
Mazzoni.
Or Tony with an I. Yeah, it could be either.
Sorry, carry on.
Tabitha. Okay, Tabitha, the gender fluid Tabitha. Okay, that's all we'll go for. Yeah, she fancy. But
They fancy.
oh, sorry, they fancy. I forgot my pronouns. Now, back to the issue at hand. Tardigrades are basically freaking awesome. They can survive in so many harsh environments, and they really make a great example organism to have a look at and to sort of figure out what we can maybe be looking for in terms of life on other planets. So previously we've talked about extremophiles on the show, where we've talked about, oh, these are organisms, very often microorganisms like bacteria or archaea, which are single-celled organisms, and they live in extremely intense environments, such as volcanic vents at the bottom of the ocean. They live in freezing cold temperatures, very arid, dry environments, or very salty environments.
Earth crust and also an arsenic lake in Yellowstone, I think.
Yeah, and like those examples of life, those are some examples of life that we didn't think possible before because they survive without what we would consider vital elements such as oxygen, light, and those kind of
Phosphorus.
things. Phosphorus
the
as
one
well.
for the arsenic. But we need to make, there is a difference between extremophiles and our tardigrades because extremophiles thrive in this environment. They are perfectly adapted to live in this extreme environment. Tardigrades just have the ability to survive. They are the ultimate survivalists, and they are brilliant at it.
Yeah, and they do get given the term polyextremophiles, which sounds like they've got a bit of kink to them, but they are not technically extremophiles, as Alf just mentioned. So what these amazing little creatures do, they actually look adorable, just don't look them straight in the mouth because they got some freaky little toothy proboscis going on there. You don't want to get on the business end of that. But, yeah, you really don't. But basically, when times get tough, they will literally just go to a state of a suspended animation and wait it out until stuff gets better, so they're actually kind of lazy. And
you call it lazy, but they're just surviving.
They just survive. Woo! Their survival is, doesn't seem to require much effort. A recent example has been that researchers have recently dug out some stocks of tardigrades that have been frozen solid for more than 30 years, thawed them out, and they've sprung back to life. And that's because these amazing little creatures, even though they normally, like us, enjoy living at temperate environments, with the water about 22 degrees, living in moss, lots of happy things to eat and that kind of stuff. They can produce this fatty substance which basically protects their cells and stops ice crystals forming and destroying the cells. Because you may have heard of cryogenics, and there's all sorts of crazy rich people, and I hear Walt Disney is one of them, who has decided to have... Or either him or his brain.
No, I think that's a rumor that his head is frozen.
Well, it is a rumor that I like to perpetuate because I think it's interesting. But there is actually a lot of rich people, whether Walt Disney is one of them, I don't know. Oh, that was good. that was a good little reference you got in there. But yeah, so there's a lot of people who think, oh yeah, let's cryogenically freeze ourselves, and we'll be able to be revived one day, but I'm afraid not, because ice crystals will really mess you up. If you'd like to see this for yourself, go freeze a tomato, then take it out and stick it on the side of the counter and see what happens. It's basically like freezing a living thing effectively is like having a load of knives appear amongst a ball pit of balloons. Bad stuff. Well, that's not quite the time that we're playing.
That's your use of analogy.
Oh, thank you. Okay, my use of analogy, yes. But these tardigrades are amazing. They produce a lot of this fatty substance that protects their cells and stops these ice crystals forming. And also they form an interesting little ball called a pun if they run out of water. So they effectively dehydrate themselves and produce a gel that slows their metabolism down right the way down to 0.01% of its normal activity. And that is almost the equivalent of us humans taking about one breath and a couple of heartbeats every 6 to 8 months, and still being okay. I half worked it out last night, but again, we've already just touched on how bad my maths is, so please go and double check that. But yeah, they're pretty badass, and they've even been taken into space, where they've been exposed directly to solar radiation, which we're protected from here on Earth by the Earth's magnetic field, and they were brought back down to Earth, and at least 60% of them sprang back to life, well, sprang back into animation, and went on to have happy families and little baby tardigrades. And really, they're insanely adaptable. So if we were looking for life on other planets, not only could we be looking for extremophiles that thrive in such strange and extreme environments, we could be looking for animals that may be enduring what we are seeing as harsh times in a certain planet's environmental history. So, for example, Mars, we know, used to have flowing water, and at that time in its lifespan, Mars may have had extremely habitable conditions, which it doesn't anymore. And so, who knows if there could be some life like tardigrades that are just waiting out the tough times. They'll probably wait a very long time. in some instances of the very salty water that has been detected on Mars.
The issue why it's important to look at tardigrades in space is the fact that they can survive radiation. As far as we can tell, the Earth is quite unique. I mean, it's very strong magnetic field, and most planets that are around in the Milky Way are around red dwarfs, which are a lot more active than the Sun, so emit a lot more particles. So their star winds is a lot stronger. So it's, if we can understand how creature can survive radiation, could give us an idea of how life can survive out there.
Yeah, and it's just a very interesting area of study. The last sort of fun fact I'll give you about tardigrades, because I could literally talk about them for days, as I literally talked about them all night last night. No, I promise.
The shade.
You are a guest on this show. I will have you know. We're getting just so much like shady banging from it tonight.
Didn't intend it to be that way.
Anyway, I've lost my gold star. Anyway, yeah, tardigrades are just absolutely fascinating, and the one of the trick they have up their sleeves, which is perplexing in so many ways, is they undertake something called horizontal gene transfer, and it's a very interesting process by which one organism will take a little bit of genes from another. You only normally often see that process in very, very old organisms like archaea and very primitive organisms. And some bacteria, and basically it's where organisms take a few chunks of DNA and they swap it between each other, and they will incorporate that DNA into their own genome, and in some cases they will use it. So in the case of bacteria, we see that happening where antibiotic resistance is conferred from one type of bacteria to another, or to different types of bacteria from other colonies. So that's why a good reason why you should finish your course of antibiotics. Yeah, I'm finger shaming you all. But tardigrades do this from all sorts of creatures in their environment that aren't even the same species or even closely related to them. And some recent studies have suggested there's probably between 9 and 23% foreign DNA in the tardigrade genome, which is just astounding because no other multicellular organism, as far as we know, or at least as far as I know, can withstand such intrusions effectively into their genome and still have a stable genome, and in terms of something that still works and still makes them a tardigrade. Because I don't know, it's not like they take on a quarter of genes from other animals and it's like, oops, no longer tardigrade, I'm kind of a half plant bacteria tardigrade. It doesn't happen like that, but it makes them extremely variable, and variation is of course the spice of life.
Yes.
And it is indeed, and yeah, they are just awesome. So, if we're looking for aliens on these weird worlds, such as your three-star body system, who knows, it could be a tardigrade. Also known as a water bear or moss piglet, which is freaking adorable.
Moss piglet, that's sweet.
It is, isn't it?
How about, since you write a book for days about tardigrades, you answer a couple of questions. I'm getting good now.
Yes, thank you. I thought I was friendly and informative, yet I'm just getting shot down.
So I've had some questions from Jamie _Cockcroft, and he has asked a number of things. One question he's asked is, will we ever know the neural markers of mental disorders?
Ooh.
Mental illness. I am going to say no to that, or at least no until we get our act together with how we think about diagnosing mental disorders. So in my field, for example, in children who have developmental problems, the diagnoses that we give them are really important for them and their families, but in terms of research...
Sorry, I'm not laughing at you, okay. But we just had a tweet from @kcog_, who's finally changed his name from G&T to Greg. So, hey Greg, he said, tardigrades, they're so tardigrade, which I just love.
Okay.
Thank you. Thank you for affirming my obsession there. I'm going to retweet that. Thank you.
So, as I was saying, that the diagnoses that we give are really important for the children and their families, but they're not always so great in research terms, and that's because you can get you can get two kids that have the same diagnosis who are radically different, and you can get two children who have different diagnoses who are incredibly similar. So the diagnoses are not always very specific. And children often will meet the diagnostic criteria for multiple diagnosable problems. And essentially the way that we do the diagnosis, I think, isn't really fit for purpose. And the problem is that as long as we think about these things as being discrete diagnoses, these discrete groups of kids or cases that have particular symptoms and they're separate from other kids or cases with different symptoms, as soon as we keep thinking about it like that, we'll never get anywhere close, I don't think, to understanding the brain mechanisms behind the problems that they experience. And that is because these diagnoses are not like a diagnosis of gout or something like that. They have symptoms that are in common, they have symptoms that are separate, and until we realise that these things are just on dimensions and that those are the important things, rather than whether you fit into one category neatly or another, whilst we persist in the way that we're currently persisting, I don't think we're going to get close to understanding the neural mechanisms of particular disorders.
So when you talk about neuronal markers as such, what kind of things for, say, mental illnesses would you maybe expect to find? Even if you just give an example for a particular kind of mental illness or mental affliction. Okay.
So the example that I probably deal with most is children who have a diagnosis of ADHD, which is relatively common.
So that's attention deficit
hyperactivity disorder. Thank you. Yes. So people have often said that those children have problems in the frontal lobe because they have experienced problems with inhibiting responses, inhibiting inappropriate behaviour, staying on task and attention. But the reality is that we know that most of those children, or many of those children, will meet all sorts of other diagnostic criteria like the Tourette's, OCD, obsessive compulsive disorder, or autism spectrum disorder. Also, many of those kids will have symptoms in common with kids who have very poor working memory, for example, who have no diagnosis whatsoever. And the point is that you shouldn't be looking for neural correlates of ADHD. That's a kind of meaningless thing to do. You should be looking for neural correlates of the symptoms that those children experience. And of course, those symptoms are maybe experienced by lots of other children who don't have the diagnosis. So as soon as you start saying that, then you're starting to say, well, maybe the diagnosis isn't all that important in research terms. So yeah, and I think if we keep persisting with this idea that you do a study and everyone has to have the diagnosis, and it's a bit of a fudge really. It's not really we all know that that's not the real world. And as long as we keep going along that route, I don't think we're going to get close. Thank you.
So something to think about. While putting things into boxes may always be useful to us as human beings, as we all like to do, life is all very often more complex. It's dimensional. Oh,
Dimensional is the word we use.
It's dimensional.
What is the second question?
Oh, I can't remember.
Okay.
The second...
Unless we got a question from JD?
Oh, yeah, we have another question from JD. Let me read it first to make sure it's safe for... No, of course it is. Gout. When did we TARDIS back to the 17th century France?
I was just trying to think of an example.
Hashtag TARDIS grade.
Another question.
I love it. You get a gold star from me, JD.
Another question that Jamie Cockcroft had is what are the main problems with conducting neuroscience research? There are like 1,000 that I can think of.
Oh my god, yeah.
One time I had a guy turn up to do an experiment who was drunk.
And that's just with humans. And by the way, as you might be able to tell, I am loving it tonight because the astrophysicist is finally outnumbered with a fellow neuroscientist here with me.
Yeah, but my galaxy never turned out drunk. There is alcohol in space, but it's...
I would be concerned if your galaxy did one day turn up drunk behind the microscope.
I didn't initially realise that he was...
Telescope!
I would be concerned that there's a galaxy in a microscope.
I didn't initially realise that he was drunk, just for the record.
Oh.
And then we were halfway through the experiment. I thought, this guy's terrible at all of the tasks. And the activity that we're recording is just all over the shop. And then he came out and he couldn't kind of walk straight. And he was kind of very sweaty. And I said, where did you go before you came here? He said, I was at the pub before I came here. And that's when I thought, now it all makes sense.
There's the outlier right there.
Yeah, he wasn't included in the
But yeah, the problems with conducting behavioral neuroscience research, it's like an endless question.
Recruitment's a real pain.
Especially when you talk about the human side of things.
Yeah.
Even when you talk about the animal model side of things, it gets very complex because animal models, while they're very useful, because they provide us with an easy way to manipulate and essentially control more variables than you can with humans.
Yeah.
Again, they aren't humans, but there's a lot of ways in which they're similar. But at the same time, when you are drawing parallels between, say, it's very commonly used mice and humans, especially with behaviours, it's very difficult to say which behaviours are equivalents. So a good example of that is fear or anxiety in mice. To work out what mice do, which we would interpret in an anthropomorphic sense as, or a very humanized sense as, oh, this mouse is experiencing fear-like behavior, we don't know whether it's fear in the same way as we would have fear. So really, we're kind of going on our best guesses in that. And that actually, it makes it sound like it's all really bad, but I mean, it's just another tricky thing to navigate that you have in every field of science.
I love that the problem in, at least my branch of astrophysics, is that we have too much data. This is why we use...
brain sciences as well.
Yeah, this is why we use citizen scientists, and actually go and do Galaxy Zoo or Planet Hunter, because we need people that can spend half an hour a day or 10 minutes a day just helping scientists, because we have so much data that needs to be classified, and not enough scientists and not enough money to actually spend time doing that classification. And you know, come on, do it at work, so it's much better than work.
Yeah.
It's much better to outsource, and there is actually a really interesting one, which I'll tweet about after the show, where I think it's NASA are trying to quantify interesting landmarks on Mars, and so basically you just look at a couple of pictures of Mars and you try and highlight a few things.
Yeah, apart the crazy people that you see, there are crazy people saying that there are churches on Mars. There's no, don't boo, because it's actually crazier than that. There is a conspiracy theorist saying that Jesus first appeared on Mars and then he punished the Martian and turned Mars into a desert and then moved to Earth. Thank you. And so, if these crazy people have enough time to help NASA, please find 10 minutes. Please find 10 minutes.
I think one thing that's really good in the last 5 years or so is this whole thing about open data, where there are large data sets that are freely available to anyone to download and analyze if they want. So like Human Connectome Project, for example, really large, massive data sets that would be way too big for any one person to properly get to grips with. But the point is that if you wanted to, you could download, X hundred subjects. And the data are freely available. And I think that's obviously the way forward.
It's the same in astronomy. There are few projects that are completely available to the public. They can go look at pretty pictures and get data. And this is fantastic because people like me that I'm a scientist but I'm not in academia anymore can just go and say, oh, this is interesting. Is anyone doing something about this? And can have a little project. Most of the time it's just like, oh, okay, this question has already been answered, but sometimes maybe you get lucky and you have something interesting to talk about. And it's wonderful. The open data allows science to be, as it should be, completely free of the fictional borders and fictional institution that we put on science.
And ultimately, in most cases, it's the taxpayer that has paid for the collection of the data. So they have...
So we
it's
have
in their interest for it to be maximally made benefit of.
Absolutely, and it brings up the really moral question of is the pursuit of knowledge worth it if this knowledge can't be shared? I mean, what's the whole point if, say, we got together, got loads of public money, did some amazing research and some really cool stuff, but you never allowed to know anything about it? Why would you trust scientists any further? Why would you give them more funding? Why would you say, oh, they're useful in the world, if we were just to keep it to ourselves? So I'm all personally, and I think we all are here, all for more of the open data.
Yep.
And some journals now, when you publish it, they want you to upload the data so that anyone else having read your paper can then access your data, run the analysis for themselves, run different analyses, and there are kind of various levels of open data open source data that you can get. You can get a rubber stamp on your journal, kind of badge of honour.
This is the future, guys. The future of intricate science.
It's very interesting. We are past our usual time, but I have the last piece of news. If you want to do that, unless you guys want to contribute.
No, well, we had one last comment from Twitter from JD who says, make a Twitter poll please to vote on my next hair colour. Yeah, I'm always open to suggestions, but I'm sorry if I'm boring you all with my normal hair colour.
Is this your normal hair colour?
It's as normal as it's going to get. Deal with it.
Alright. So, the last piece of news is another simulation. So,
A what?
another simulation.
Okay.
So, while you...
Another simulation. Enunciate. Enunciate.
That was a bit German. Yeah, you see, you're being booed. Anyway, the simulation is looking at the universe on large scale. There is a big problem when it comes to when we look at the universe. As scientists, we just need to repeat our experiment over and over, but we have one universe. So how do we go about repeating the experiment? Is we create computer models and simulations, and we look at how they evolve when we change some parameters. And what the simulation came up with is reconstructed a cosmic web. Say with question, what is the cosmic web?
Yeah. Okay, look, I thought you were looking to me to explain the cosmic web. I'm like, hey, I don't know. That is like,
darling, you couldn't explain the right-hand rule.
Excuse you. I knew that.
Thing.
I knew that we love each other really. I knew that the three-finger was about right angles and stuff and magnetism and.
Anyway,
whatever,
the cosmic web.
We all have our uses.
With the cosmic web is how matter and dark matter is distributed across the universe. They're not distributed uniformly. It's uniform in very large scale, but dark matter and normal matter, what we can see, is distributed in filaments, which create the cosmic web. And across those filaments there are voids, and they form at the very beginning of the universe due to complex and boring quantum fluctuation. They're not boring, but they're boring for this too. Oi! Anyway, what happens is that there is, of the things we can see, so tables and people and stars, about 20% of the matter is missing. We don't know where it is. And the simulation actually tells us that supermassive black holes are able to push that matter, the visible matter, into the voids. And we should be it's complicated to look because, once again, it's stuff that is very cold in a place that there's nothing else to interact with. But it's a good idea that we can understand how the universe on a large scale works. And it's another step into sort of work out why the universe is the way it is. So that was all for me and the world of astronomy.
Thank God. I'm kidding. We love space. We do.
Yeah, because this is called the Astroholic.
Yes. We all know. Just let me have this moment of having the biologists outnumber the physicists. Thank you. He's going to let me have this moment, I think.
I will. And with that, I think we can conclude for tonight.
Yes, I think we've covered quite a lot of ground.
Yes.
Thank you very much for having me.
Oh, it is more than welcome.
Thank you for the wonderful cocktails.
Yes. Thank you to always.
Thank you to the Merlot grape juice.
Merlot grape juice. That definitely made it.
And thank you all for watching. I'm Alfredo Carpinetti.
I am Matt Young, and special thanks to our special guest today,
Dr. Duncan Astle.
Yeah. If you want to follow us on Twitter or find out anything else about who we are, what we do, I am at MattJY. You are at
Duncan Astle.
Duncan Astle.
I'm at Dr. Carpinetti or at the Astroholic, and please stalk us.
You are, we have actually just extended the invitation to you to stalk us because we love meeting new people that way.
So have a great night and see you at the next
Sorry.
Have a great night and see you at the next Astroholic.
Thanks.
Thank you.